Just a quick history behind BAR Technologies. In 2017, BAR was formed to compete for the 2015. It was actually formed to compete for the America's Cup that was held in 2017, and that was the Land Rover BAR campaign. And out of that, at the end of that campaign, BAR Technologies was spun off as a commercial entity to take advantage of the America's Cup technology, leverage it in the industrial space. So just a little bit of context there from where this presentation comes from, and then also at the end of the presentation, we're looking a little bit at the commercial implications of the work. But just to say as well is that I need to give a lot of credit here to Maddie, Matt, and Martin for the work. Most of the work that I'll be presenting has been done by them. I'll also probably be referring the more technical questions to them as well. But just as a quick lead into this, just be going through I think a little bit of context behind the America's Cup probably served quite well in terms of the problems that we encounter. I'll talk about the AC75 Yacht as well. It was a pretty special yacht in that it was the first version of a pretty unique vessel. I'll talk about the loadings. The presentation is mostly focused on the dynamic loading analysis that we had to do. It was, again, pretty particular to this type of vessel. And then, as I said, looking towards the practical application to commercial vessels. So as far as the dynamic loading is concerned, we've split that up into three phases really, and I'll go through each of those, being sort of the first initial validation phase, the preliminary hull studies, and then quite a detailed investigation of one of the principal areas of the hull, or the platform, as we tended to call it. Right. So just as far as the America's Cup itself is concerned, it's the oldest international sporting trophy that's still ongoing. Started in 1851 with a race around the Isle of Wight, which the Americans won, and they managed to hang on to that until 1984. And after that, it's changed countries a few times. It's held approximately every 3 to 4 years, and that's because the format of the competition itself is quite unique, in that at the end of each competition, the event is effectively reset, because the rules for the next competition are set in agreement between the winner of that cycle and the challenger for the next one. So you have what's called the challenger of record, and then they come to an agreement about what particular class the boat is going to be sailed. What particular class? What I mean by that is the type of boat that it's going to be sailed in, and that could be entirely new, which was the case the last time around. The location could also change, so the conditions change, and then the system of scoring and the format of the racing can also change. So it's essentially a blank slate. You do have what's called the deed of gift, which governs the basic conditions, but other than that, the entire technical specification for what's involved can be radically different from the previous cycle of the competition. One characteristic of the event is that it's always trying to leverage the latest technology, and that's been right from the beginning. Depending on who you have a discussion with, the sailors will disagree with the technical guys that the fastest boat is always going to win. But that's generally the case. It's as much a sailing race as it is a design race. We're always trying to get hold of the latest, greatest stuff that's going to make the boat go quicker. And right from the beginning, when they had the original race around the Isle of Wight, that was run by a boat that had superior hull form and also superior sail technology. So it's always, it's always been the case. The rules do limit the design to some extent, and that again depends on the agreement between the competitors. But the timeline is typically very tight. To give you an idea, a boat of this type takes approximately 6 to 8 months to build, and you've got to have your development pretty much nailed by that point, because it's locked in. It's fairly locked in from once you start to actually produce physical components. So the race always starts right from the beginning. So trying to leverage the latest simulation technology and so on is always front and center. Just as far as the yacht itself is concerned, so this was an entirely new class of yacht. The 2017 generation of boats were foiling catamarans, and they foiled on 3 hydrofoils with a solid wing sail. The new class of boat was a foiling monohull, which no one had really done before. No one was sure it was actually going to work until the first prototype hit the water. These boats are fairly large, 75 foot long, total mass of around 7.5 tons, and 3 hydrofoils. And you're only foiling on 2 hydrofoils, so the one being the main foil, either port or starboard or left and right, and then there's a hydrofoil on the rudder as well. Instead of the wing sail from the previous generation, they have what's called a double skin sail. Again, a new invention for this particular boat. So normally a yacht sail is a single skin, but by using 2 skins, they create a more effective wing shape, which in theory was a lot easier to handle than the solid wing sail from the previous generation of boats. They're very efficient boats, and in the last Cup, they were seeing top speeds in excess of 50 knots. And with the next generation of boats, we should expect to regularly see that number being exceeded. A lot of people ask, how do these things work? It's a little bit of an awkward looking boat, but basically you've got a heeling moment which is generated by the side force on the sail in order to produce, just like any other aerodynamic surface, you're producing components that are in line with the direction of travel of the boat, which is your thrust, and then the side force on the sail, which is trying to heel the boat over. What counteracts that to some extent is the main foil lift. So that's keeping the boat above the water surface, but then also providing righting moment together with the mass of the yacht. Obviously, the more leverage you have on the foil, the higher the thrust you can generate in the sail, and that's really the basics of it. Just in terms of the loadings on the boat, I'm not really at liberty to talk too much about the actual numbers, but just to give you an idea, the primary loading on the boat is generated by the aerodynamic loads which are fed into the boat through the rigging of the boat. And what it really boils down to is you've got fore and aft loading, so front to back, trying to keep the sails in position. That can generate, and then together with the transverse rigging, keeping the mast upright, that can generate approximately about 60 tons of load on the mast, between 60 and 70 tons. And that's trying to bend the boat in half, basically. So very high loads. In terms of the design and construction of the boat, all the primary structure is really manufactured from composite materials. There's very little that's not composite on the boat. A lot of the materials that are being used today, if it's metal, it's often printed components. It's a very open design rule. So in the past, the design rule was quite closed. You had limited, you had prescribed weights of skins and so on that you had to meet. This iteration of the rule allowed a huge amount of flexibility. What it all boiled down to really was that you could have as long as you met the minimum panel weight rule, which is 2 kilos per square meter, which is really light, you would satisfy the rule. There's also a limited amount of structural testing required as well as part of the rule. So it gave the designers a lot of freedom in terms of coming up with the optimal design. The primary structure is also completely hand-built. It's subject to a very strict mass budget. The rule stipulates that your boat will weigh a certain amount within a very tight margin. So each area of the boat, typically, its systems, structure, and so on, will get a specific weight budget, and you need to stay within that weight budget. To give you an idea on the structure of the boat, what you see there is the platform, what we call the platform. So this part of the boat here, which holds everything together, weighs just a shade over one of the foils. And the foil weight is governed at around 1.5 tons. So it's an extremely lightweight, very fragile structure. So you end up making use of extensive simulation on all aspects of the structure, and then doing as much optimization as possible within the time frame that you have. Right, getting into the subject of the presentation, and that's really to do with this, with simulating the dynamic effects on the hull. So this class of boat introduced an entirely new set of load cases. Being a foiling boat, it operates at very high speed, and it tends to come off the foils every now and again. And if it comes off the foils, basically it means that the sailors have lost control of the boat, and it's the equivalent of a crash. It then crashes into the water, and it could crash in any attitude. This is typically what's called a splashdown event, so lost lift on the foils, and the boat immediately then comes down into the water. A more extreme version of this would be what we term a stuff. So again, loss of control. In this case, the rudder comes out of the water, the boat's not able to hold the back end down, and the boat pitches forward under the action of the thrust in the sails, and that drives the boat into the water. So you've got 7.8 tons of boat that's originally doing 75 kilometers an hour, decelerating within the boat length. In this particular event, the boat actually popped out backwards. So very high loads being generated in these events. So looking at the aims and the methodology, so really what we were aiming to do was to use simulation to develop our confidence in the use of the tools and to prove out a structural concept. As I said, we needed to create a boat that was as light as possible. So we needed to understand the simulation methodology and how that worked in terms of improving accuracy, and then use the results as input into designing the actual race boat. The methodology involved this, as I said, a phased approach. So the first model was really looking at the feasibility of using the technique. The second model was to confirm the full platform hull structure that we would design the race boat against. And then the third model focused on the specific area of the bottom of the boat, which I'll explain in a little bit more detail. Just to say as well that in all the cases we used an explicit solver, and that was basically the Alice Steiner ALE approach, so the arbitrary Lagrangian Euler method. We did consider using CFD tools coupled with our structural tools, but that would have required quite a large overhead in terms of developing that tool chain. So we went directly to GRM, who kindly helped us out with the explicit analysis for this particular problem. So just looking at the FSI model itself, so we'd already been sailing. We'd already built our first version of the yacht. The rule allowed you to design and build two prototypes. The second one being your race boat. So we had quite a bit of data that had come out from sailing the boat. So we decided to, in effect, model the boat against a known condition and look at the outcome as it and compare that against the real world data that we'd recorded. This was a simulation that Martin did with his phone and a bathtub, which was really interesting and just aimed at validating the approach. So qualitatively, it looked appropriate. It looked good. Also, the results, although a relatively really simple experiment, they showed that we're on the right track, and we had confidence in moving into the next phase. Really, so really cheap, simple. Merrick's Cup's really not known for doing that, but it was definitely it added quite a lot of confidence And then looking at the preliminary setup, we took the what we call the RB1 model, set that up in an initial state that reflected an event that we had recorded. The boats are well instrumented with inertial measurement units, strain gauges, so we had a lot of data to compare with. Just looking at the response of the boat in that scenario, it looked reasonable. We were happy with those results. It was a fairly coarse model. The structure of the boat, as far as the composites were concerned, was well represented. But obviously it excludes the rig, so we're not capturing the full inertia effects of the rig, and also the foils. They can have a significant role, but we decided to exclude the foils due to the complexity that introduced into the analysis, and we thought we could compensate for that as well. What was more valuable was looking at the quantitative results that we got out in terms of the global response of the platform in the event, and that tied in quite well with what we had recorded on the vessel, and that gave us confidence to move forward. We also looked at the distribution of the hull pressures as they evolved in the event, and again they pretty much confirmed what we had used as design pressures. So just to sum up on that, the first phase was fairly successful. We were quite happy with the way that the tool predicted the hull pressures, which was really the main aim of the analysis. There were various, I'm not going to get into the details of that, but there were various parameters that needed to be tweaked that would then enable us to have confidence moving into the next phase. The next phase involved the RB2 shape, so that was substantially different from the RB1 shape. So you can see the fairly radical longitudinal keel type structure, which we call the bustle. So the volumetric distribution is quite different, and the way that it impacts the water surface is therefore very different as well from the RB1 type model. In this particular case, we added the rig component to the model as well, to increase the fidelity of the simulation. Again, in order to assess the response of the hull, we set it up in initial condition as we did for the first model. So looking at the simulated results, they all looked quite realistic. And from that, the pressure results were then extracted and used to define the overall what we call the scantlings or the specifications for the laminates for the hull. You can see towards the end of the analysis that there's that particular wave that was quite an important outcome that we would not have discovered had we not done this particular work. Right, now getting on to the bustle. This was a lot of work went into this. You can see from the background image there that the bottom panel of the boat is extremely flat. That made us extremely nervous. We had multiple arguments between the aerodynamicists and the structural guys, and as usual, the aerodynamicists won because it was deemed to be a very it's a high performance issue. So we had to come up with a solution for generating a lightweight solution for a large area of the boat. So optimizing that for weight was crucial to meet our weight budget. But as I said, there's approximately 60 to 70 tons of load on the mast trying to bend the boat and break it in half. And all of that load is carried in that panel. So it's vital that we had really good confidence in that panel's ability to take the dynamic loads. So sorry, let me just go back. We considered 3 options here. And this was a straightforward panel supported by bulkheads. We introduced different stiffeners. As you probably cannot see that, but there are stiffeners in each bay with slightly different geometrical characteristics, heights, widths, as well as layups, and then a more closely spaced version of that as well. This is typically what you would get if you were designing the structure to standard codes. This type of structure here relies on the membrane effect of the panel to carry the loading. So depending on the nonlinear characteristics of the nonlinear response. This is just an example of the strains that are the pressures. In order to represent the preload that's put into the boat with the rig, we had to introduce initial strains into the model. You can see that as the boat gets, as the panels in effect get smaller, the pressures increase. Those are the deflection results. Not particularly interesting. These graphs are the acceleration reaction forces, and it just indicates that the more closely spaced panels typically have higher accelerations. So everything was driving us towards minimizing the internal structure in the bustle. We also looked at, we obviously, as I said, once the boat comes off the foils, you're into a crash situation. So you don't have much control over the attitude of the boat. So we were interested in finding out if you varied the pitch and the roll attitude of the boat prior to impact, what effect did that have on the bustle loading. And what was interesting here was that in the pitch case, it was substantially influenced by the pitch angle, which you'd expect. The flatter response generating the higher acceleration loadings at around about 12 G on the panel. And then the roll response, much less sensitive to that, but very similar maximum acceleration loads. That kind of sums up the same situation. So as your rotation angles in both pitch and roll increase, you're lessening the acceleration. But essentially, we had to deal with that point over there. This is basically what it boiled down to. It's a nice little animation that shows the evolution of the panels as the pitch angle changes. But basically, we took these results, we took the pressure results and applied these to a higher fidelity, a model with a lot more detail for the breakout structural work that led to the final design for the bustle. So just to wrap up a little bit, I just wanted to talk about the application to the commercial vessels. That work is obviously done in the rarefied world of the America's Cup, where you can afford to expend quite a lot of resource. That similar situation doesn't really exist in the commercial world, where the pressures are slightly different. But having said that, it's important still to leverage as much as you can to take advantage of what's developed there. BAR Technologies are currently developing a crew transfer vessel for servicing wind turbine farms. It's quite different. You'll see on the next slide that it's essentially a proa concept. A lot of the vessels that are employed in this particular field are catamarans or monohulls. They basically ferry the technicians out to the wind turbines. And there's a comfort level involved, and also a seakeeping limitation involved. So the vessel that's been designed is a foil-assisted vessel, so it makes use of foil technologies pretty much the same way as the America's Cup boat does. But the aim there is to increase the comfort, is to use that as a response to increase the comfort of the vessel and also increase the seakeeping qualities of the vessel. But having said that, it's quite a different concept. It's a proa concept, so the design rules that are typically used and have evolved over time don't quite cover these type of vessels. So you need another way to assess the safety, or let's say the structural integrity of the craft. So again, weight is important. It's a foil-borne vessel, so keeping the weight down is important as well. So this all points to potentially larger dynamic loads, and it's very important to understand the impact of those loads. You don't have the luxury of an America's Cup boat where you can potentially explore and repair. A commercial vessel needs to be out there operating 24 hours a day, and you need to have very good confidence in the outcome. So I'm not sure if these videos are playing. Sorry. Let's see. Yeah. So this initial work, looking at the sea keeping of the vessel through a series of waves, just shows you the potential for developing quite large hydrodynamic loads on cross-deck structures and portions of the hull. And we're currently working on using explicit type analysis codes in a similar way to size the structure and make sure that the structure is fit for purpose and safe. So just to wrap up, so we've basically used the simulation tools to good effect to predict the response of the hull structure to large dynamic loads. The computational methodology is demanding. We had to reduce mesh densities to make run times acceptable, which did necessitate breakout models, secondary breakout models to define the details. So speeding that up is something that we definitely need to look at. But ultimately, it was found that the methodology did provide a good level of confidence. We used it in anger in the race boat, and the race boat did work. We had an event during the racing, the final racing, which pretty much replicated our worst case scenario, and we came out of that exactly as we expected. So yeah, well, in terms of the methodology and the learning, we're now applying that to the commercial vessels, and hopefully that will become an accepted process. It needs to go through the relative certification authorities, but this is where we come in and hopefully push the technology that is being used to design new products. I think that's it. Thank you very much.